My name is Christine Simpson. I'm an assistant computational scientist in the Data Services and Workflows group here at ALCF. And today I'm going to talk a little bit about running task ensembles or workflows on our systems, on Aurora specifically, and some things to think about, some strategies you can use, and maybe some tools as well. To start with, what is an ensemble? What is a workflow? In a sense, everyone has a workflow. You have some steps you take when you log into our machines to, do your work. In a computational sense, in the sense we'll be talking about today, a workflow is simply any collection of computational tasks that you run to achieve a result. Workflows can come in many different types. There's a few schematic types here, but they can have complex dependencies. They can involve many different applications. They can involve data movement within the machine or from outside of the machine as well. Workflows can often include ensembles, which today we'll just simply describe as a collection of tasks running the same application with similar inputs. So for example, if you're running, say, an application like VASP or LAMMPS, and you're just running it on a bunch of different molecular systems, and you just have a large collection of these that you just need to run, and the inputs might be slightly different from task to task, but you're essentially running the same thing on the same set of resources every time. You just have a really large number of them. Sometimes you'll hear the term bag of tasks. Like, how do you run just a big bag of tasks? One thing I'll point out, and if you have experience on our systems or at OLCF, the other leadership computing facility, our queuing policies are set up in such a way that we very much encourage users to run large jobs. So if you have a collection of, say, 2 or 4 node tasks that you need to run, you cannot run these. We do not recommend that you run these as individual jobs on the scheduler. Instead, what we will encourage you to do is to bundle this work into, large jobs on the scheduler, maybe using 1,000 or 2,000 nodes or more, depending on how large your ensembles are. Sometimes this can be a little bit of a learning curve for users, but in the long run, it will make your work more efficient. And using some of the tools we'll discuss here today, hopefully can give you some strategies for approaching this. Okay, so we're just going to start with a very simple case, and this comes from our documentation. The scheduler on our machines is PBS, as Marta, was describing to you and giving you sort of some simple examples. You might be running maybe just one instance of your application in a PBS job. Now, imagine you want to run a whole collection of tasks in the same job. This could be a useful approach if you have sort of a small to moderate number of tasks you need to run, and they have sort of a low variance in runtime. So in a case like this, what you can do is you can use MPI exec to assign your application instances to specific nodes within your job. And this is one example of how to do this. Now, depending on like the particular shape of your workload, it might look different. But in this case, when you get a job through the scheduler with PBS, you always have an environment variable called PBS node file accessible to you in the job. And what that points to is a file on the file system that contains a list of all the nodes assigned to your job. And so what you can do if you enjoy bash scripting, you can use this node file to subsample nodes and assign them to different tasks. So this is one example. Here we have this sort of complex split command. What this does is it takes the PBS node file and it creates a number of sub-node files, each containing 2 nodes per subfile. They have a name that that begins with localhost file. And so what you then do is you loop over your local host files, and for each local host file, you run an instance of your application launched with MPI exec. In this case, maybe this application might involve, message passing. In this case, this is just Hello Affinity. You can get examples of this application from our Getting Started repo if you just want a test application to, explore things like this. It can be a useful tool. In this case, what we do is we're launching, 24 ranks, so 12 times 2. We're running 12 ranks per node. There's 12 GPU tiles per node on Aurora. That might be a common thing you do. And this is the key here. We have this host file option. Here, this tells this MPI exec call to place this application on these nodes specifically. And in this loop, we include this ampersand. And what that does is it backgrounds the process. And so then you can loop through these, relatively quickly. There's some delay, and we can talk more about that. In launching all of these, you can launch all of these, in this case, just 4 tasks. We're running this on 8 nodes, 2 nodes per task, and we will let them run. When you're backgrounding your MPI processes like this, it's important to include a wait so the script doesn't return before those processes return themselves. And in this way, you can launch, multiple tasks on unique nodes that will run in parallel within a single batch job. So just to maybe pull out a few things I mentioned or I pointed to in that example, when you're running MPI exec, you can specify the nodes you want the exec call to launch your application on with either, in that case, we were using the host list option where you pass a file containing the host names. You can also use an option called hosts, which you can just assign the node names in a space separated list if you wish. And here's like two examples of these 2 different ways of doing this. Now, this is all well and good. And for some people, this might be all you need. However, there are some limitations to an approach like this. So one thing to point out is if your task run times vary, say you have an ensemble where there's one task that takes twice as long as all the other tasks, what will happen? Well, the bulk of your tasks will complete, but this one long-running task will continue running. All the other nodes that the other tasks were running on will now be idle. And this one long-running task will continue running. Because in this example we were showing you, you're just launching tasks. You have no way of refilling nodes if a task completes, right? And so you can get potentially very poor node utilization, and you will be charged that time against your project, which is not something you want to do. You want to make good use of your allocation time. Another thing to point out is sometimes these task ensembles, if you're sort of launching them all from a single node, you can run into bottlenecks. So if every MPI exec call you're running, you're actually running it on one of the nodes in your allocation, and that process is sitting on that node and it's using resources. It's using maybe it has to use a certain number of file descriptors. it takes up it's running a process as well. I mean, it might take up, a number of different resources. The big one is file descriptors. So we've seen situations where people launch a large number of MPI tasks on a single node and they run out. So that can be a bottleneck. The other thing to point out is that, launching individual tasks with each as their own MPI exec, that can be, um, you know, especially for multi-node tasks. For single node or for single tile tasks, it's less so, but for multi-node tasks, there's an overhead associated with that. So it can take some amount of time for you to launch all of these tasks in a situation like that. Um, the other thing to point out is just like shell programming is it's difficult to, handle like that split command was not intuitive. That was one example of how to do it. There might be simpler or different ways. But it's not a really great way of going about it. And if you have a situation where your tasks involve dependencies, like it's really hard to sort of manage that in a shell script. Also, you might want things like checkpointing functionality. You might want some kind of automated task logs or, the ability for tasks to automatically retry if they fail in certain ways. So, if any of these kinds of considerations are things like you've encountered or you rings a bell for you, this might be a situation where you want to consider using a workflow tool. And so we'll discuss a little bit about what that entails. So what is a workflow tool? So, I mean, it's simply any piece of software that can orchestrate a workflow. And so, um, what can a tool do for you? It will, like the ensemble job, it'll allow you to run many tasks concurrently, but also you can run them, one after another with dependencies. And you can also maybe orchestrate your workload from a single, script or process across multiple batch jobs. So if that is something that you have a need for, that this is something many of these workflow tools can do. You can manage task dependencies. You can also automate sort of error handling or restarts of tasks. If you know, like, oh, sometimes, the CFL criterion we violated, and we just know that we just need to reduce the time step by 20% and restart. Like if you know that's like a common way certain number of your tasks fail, you might just, some of the workflow tools allow you ways to implement code to sort of automate that. So, you don't have to handle this. Um, and also they can incorporate data movement. You know, for some of our workflow users, they might be moving data onto the machine. And from there, launching tasks, there are ways in which you can trigger jobs to start when like data arrives on the file system. There are workflow tools we have that can enable things like that. And so I will just say, like, there are many tools with many different types of functionality, and I can't really cover all of them. I'm going to focus today in this talk on a tool called Parcel, which is developed at U Chicago and Globus Labs, and it's a tool that's been very successful running on our machines. Has been involved in Gordon Bell efforts, things of that nature. On the right here is an example from a paper that was using Parcel to create synthetic sky images for a telescope survey, testing. So let's shift gears and talk a little bit about Parcel. So what is Parcel? It's a parallel programming library for Python. So this is a Python-based tool. You can install it with pip. So if you wanted to create an environment with Parcel, you would just need to activate our frameworks module, and you can create a Python virtual environment where you can pip install Parcel. You can run now, even though it's a Python-based tool, you can run any application with Parcel. So obviously you can run native Python functions or applications, but there's a way in which you can create what's called a bash app that will execute any command line command. So this could be running, instead of return echo, I mean, these two apps here are both running hello world. They give you the exact same result. One's the Python app version, one's the bash app version. For this bash app, you can replace this with your call to NecRS or LAMPS or GROMACS or whatever compiled application you're running. And you would just include on this line in this string the inputs, which you could pass to this Python function as as inputs to the function. So one thing to point out is in Parcel, your workflow is contained within memory. Now where it's contained in memory, you have a choice about that, and we'll talk a little bit about different ways of configuring Parcel. But another thing to point out about Parcel, which can be good for portability and also certain kinds of flexibility, is that the description of the workflow, like the applications, the apps, the tasks, the dependencies, all of that, that exists separate from the configuration. And we'll look at an example configuration, but essentially the configuration describes how tasks are assigned to compute resources, to nodes, to GPUs, to CPUs. The apps, okay, so I think I've covered most of this. I just will say it is a very active development community. There's a lot of people at ALCF and Argonne that use Parcel. They have a very active Slack. They are always very responsive to questions and very collaborative. So one thing to just talk about Parcel, and because we'll go through sort of a very simple example workflow, but one concept that maybe takes some folks a little time to wrap their head around is the concept of an app future. So Parcel is an extension of the Python concurrent futures library. So when you create a Parcel task, what you are doing is you're invoking the application, and what it returns to is what's called a future. What is a future? It's essentially a proxy for a result that may or may not yet been fulfilled. So you create the task, you then have this future. In the background, under the hood, Parcel goes out, it looks at how it's configured, and it will assign your task to run on some hardware somewhere in your job. And once that task is run and completed, the future is fulfilled and you get your result back. And so that's how you can build up workflows, by creating these futures, linking them together, and you can create, you can run just a simple bag of tasks, but you can also create dependencies. And so this is some examples where you just have here a Python app that just doubles a number. When you create these two tasks, it's not like running just a native Python function where D1 completes and then D2 completes. No, like D1 creates the future, it gets shipped off. It then immediately creates D2, creates the future, shifts off that work. And then it's very important that you include somewhere in your script a point at which you wait on the result of the future, so that your script doesn't return before your results return. So I was very, I didn't say a lot about configuring, in part because it can look many different ways, and it really depends on your workload and your application. And this is like one example, but I will say if you go to the Aurora docs and you look under the workflows and look under Parcel, you will find multiple different configurations for different situations and cases and workloads. So this is like an example, but by no means is it the only example. And really, I'm just going to go through this example to point out some features of how it looks, how it works. But of course, like you would need to this would be the place where you would tailor your how Parcel uses the resources in your jobs to execute your tasks. So Parcel will always operates on a worker model. So you create tasks, and every task is assigned to a worker to complete. So what you need to configure in your configuration is how what compute resources do the workers have? Okay. So in this example, and I will say I kind of concatenated this because for space reason, if you look at the example, this is taken from our documentation. If you look there, you'll see at the start you need to import a bunch of things. But in this sort of heart here, you're creating here, oh, sorry, the config object. And so this is sort of the key piece here. What you need to include is some description of uh, how you're going to scale your workers. So we often recommend that people use the high throughput executor for cases where you want to run maybe one worker per GPU or GPU tile. In this example config, we're running one worker per tile. So with the high throughput executor, we need to tell it um, the tile names, which are created up here, and they have this format of 0.0, 0.1. Maybe Marta covered that in her talk. I'm not sure, but this will be a list of those tile names. We're going to tell it how many workers per node we have, and this should match the number of tile names you have in this list here. So it's 12 on an Aurora node. We can then also give it a rule for how to assign CPU threads to each worker. And there are sort of optimal bindings for CPU threads to GPUs. And so we construct an object here, CPU affinity, that encodes that mapping essentially. And then one thing I will say in this case, you need to give it a way to provide nodes. So this particular config, we are assuming that we are launching Parcel's workflow from within the job. So all of the resources, all of the nodes assigned to the job should just be available. So in this particular case, we use the local provider. Now you can also run a Parcel config where you launch it from the login node and it will submit jobs to the scheduler. In that case, your provider would be the PBS Pro provider. And if you look in our documentation, you'll see some examples of how to do that. And you will need to include all the things you would include in a job script. I have some examples I can point you to. And then the last piece is just how are you launching the workers? And so essentially in this case where we just have one worker per tile, we do this with the MPI exec launcher. There are different launching strategies within Parcel. And if you go to the Parcel documentation, you can find a lot of details on that. And then also in our Aurora documentation, we have a few different options and flavors of this. Like if, for example, you want to run an MPI application, we have an example of how you make your workers use multiple nodes, for example. So just very quickly, I realize I'm running out of time. What would a complete sort of workflow script look like running Parcel? Well, there's sort of three pieces we've talked about. There's your applications, your apps, your config, and your tasks, right? And this shows you all three pieces put together. So here we have two applications, two apps, double and square. We then create a context where we load the config, and we're, in this case, using a config like the one previously where we're putting one worker per tile. And then we create our tasks. So first we create a bunch of double tasks. We create 10 of them. And then we create a bunch of square tasks, but we make them dependent on the result of the double task. In fact, they use the result of the double task as their input. And then very important, we always have to include, well, here we have uh, yes. And so here, like implied here, okay, there is a weight on the result of square because essentially this can't really be created until you square returns. But here we then weight on the results of all the square tasks before they return. And so then the end result of this script is you will just print out the results of the square tasks, and you will have completed all your double tasks, all your square tasks. Okay, so there's many tools out there, and you may have a preferred tool that you use. And you, of course, we will, if you need help getting that running on our systems, we're happy to talk with you and help you get that running. If you are looking for other tools or tools with other features, there's a whole plethora of options out there. And so, I'll just mention a few. There's a common tool at the facility called Balsam, which, unlike Parcel, contains the description of the workflow in a database, rather than containing it within memory. And so in this case, though, it has some similar features. It has a Python API. It has a command line tool. If you'd like to try out Balsam, we have documentation, and we have example exercises from our fall workshop you can take a look at. And the main thing is you need to get access to the Balsam database by emailing our support, and we can add you if you do that. There are other features of workflow tools that you might find that you need. So for example, maybe you need something with some kind of data management layer. That's something we're commonly seeing in workflows that involve coupling simulation and AI tasks. There's a couple of different options in this space, and we've played around with a bunch of them. We have documentation on two of them, SmartSim and Audios 2. We've also tested and run Dragon, which is a newer tool on Aurora as well. These might be options in this space if that's something you need. And the last thing I will say is we also have a lot of workflows that run maybe more on Polaris, but I'll mention it here where you need to couple it with some kind of remote trigger or remote data movement. And in that case, we recommend Globus Compute and Globus Flows, which actually use Parcel as a local executor. So actually, if you learn Parcel and then you find you need to do some things with Globus Compute or Flows, there's a lot of that knowledge that will transfer to these tools in particular. So with that, I will just conclude here and say that I've gone through a number of different tools and examples of different strategies, different considerations. Small ensembles, you may be able to run simply with a PBS job. And actually, I have some extra slides with some additional flavors of PBS ensemble jobs if that would be useful to folks. Um, Large ensembles and complex workflows, we really do recommend that you explore a workflow tool. I went through some examples of how to use Parcel, which is an effective tool that's we've been able to scale on our systems. There's many other tools available though, and we're happy to work with you on any tool that you're interested in running. And with that, I think I will conclude. Thank you.